Experimentally, a current balance is a simple enough apparatus. All it is a solenoid on one end that creates a magnetic field that's going to interact with a current on the inside. When it interacts with the current, it'll produce a force pushing down on one side of our balance. And just like any balance, the other side will have to have a force also pushing down to keep the thing level. So a current balance you can think of as a seesaw. One side you'll literally put masses, the other side the force will be provided by the magnetic force from the solenoid interacting with the wire itself. So the solenoid will have a current passing through it. As we vary the current, we vary the magnitude of the force that's acting on that side of the wire. And on the left, where there is no wire, we just vary the force by changing the masses. When those two forces are equal, the magnetic and the force of gravity, then we have a perfect equal arm balance. Let's look at it diagrammatically. The top view of our diagram shows our balance running down the middle. The little pivot point is right at the mouth of the solenoid. On one end of the balance is our masses, and in this case we have a mass of 0.50 grams. And the goal is to balance that force of gravity pushing down into the page from our view with a magnetic force acting on this little strip of wire inside the solenoid. The length of this little strip, this little vertical strip, is 2.5 centimeters. The current going through the solenoid, which obviously will vary the magnetic field in the solenoid itself, is set at 3.6 amps, while the current going through the wire inside the solenoid is 1.5 amps. A side view is drawn below to show us basically what's going on in terms of general torques. The left-hand side shows the mass acting on the balance, and in the middle I've drawn a pivot point to represent the seesaw. The right-hand side I've drawn a little circle to represent a side view or a cross-section of the wire. This is the wire that's got the 1.5 amps pouring through it, and it's going to experience a force. Let's label the forces acting on the seesaw and see if we can determine what the general equation might look like. On the left-hand side of our seesaw, we have a force of gravity acting down. And on the right-hand side, we want to balance it with a magnetic force. And notice we want our magnetic force to be acting down, and we determine this value with the right-hand rule. Now, as with any seesaw-like problem, it's a torque question. Our pivot point is right in the center, and the distance to the forces from the pivot point we'll label as L. So the general equation for torques is simply that the torques clockwise have to equal the torques counterclockwise. Since torque is force times distance, our clockwise torque will be generated by the magnetic force. The distance from the pivot point is L, and the counterclockwise torque will be generated by the force of gravity, and it has the same distance L. Since both sides have the same distance, we can cancel off the L itself. So we get a simple equation. When the magnetic force is equal to the force of gravity, we have balance. So how do we calculate the magnetic force? We know the force of gravity is just mg. That's simple. The magnetic force is a little bit more complicated. Let's look at that now. For a current carrying wire in a magnetic field, our magnetic force is given by the equation BIL. B is the external magnetic field. In this case, it's generated by the solenoid itself, and we'll have to calculate it. I is the current flowing through the wire, not through the solenoid. So I, in this case, will be 1.5 amps. L is the length of wire in the magnetic field. Now this gets a little bit tricky since we have a few lengths. We see a length down at the bottom running horizontally and a length at the top also running horizontally. The only vertical strip, and it turns out this is the one we're going to use, is 2.5 centimeters long. Why don't we use these horizontal strips? Well, if you use your right-hand rule, Your thumb will point in the direction of the current, your fingers will be in the direction of the magnetic field, and if you try and arrange your hand that way, you'll find that the current and the magnetic field are actually parallel to each other. The field lines running down a solenoid, down the middle of the solenoid, are also horizontal lines in this diagram. So if the current and the magnetic field are parallel, they're not crossing one another, there's no force experienced on either side of those wires. So the only force experienced will be this little segment at the end. So we know what L is. It's going to be 2.5 centimeters. So let's figure out how we can calculate B. B for a solenoid, mu naught Ni over L. We would need some of that information from the question itself. We'll give you that in a second. L in this case is the length of the solenoid, the overall length of the solenoid. Sometimes you'll see this equation written as follows. It's the same thing. It's just that little n replaces n over L. It's turns per meter or turns per centimeter, depending on what they give you in the question. In the top equation, capital N is the total number of turns in the solenoid, and L is the length of the solenoid. It's not the length of the wire. To avoid confusion, I'm going to label the two L's on the diagram and color code them according to the equation. The length of the solenoid in blue to the length of the wire inside the solenoid experiencing the magnetic force is labeled in green. Notice I've also added the 1.5 amps above the I at the top, and I've labeled I solenoid because that's the current flowing through the solenoid that's generating the magnetic field in the middle equation. The question asks, given this configuration where we know our currents and our different lengths and distances, what is the strength of the magnetic field in the solenoid to create this balance? Let's slide it down a little and do the math. Our most general equation is our magnetic force is equal to our force of gravity, and it looks like this. BIL equals mg. We wish to solve for the magnetic field, so if I solve this for B, I get B is equal to mg over IL. And in this case, our mass is 0.5 grams. We'll need to convert that to kilograms. G, as usual, is 9.8 meters per second squared. I, remember, was associated with this magnetic force. So I will be the current flowing through that segment of wire, which is 1.5 amps. And L is the length of the wire inside the field, which at the top was labeled 2.5 centimeters. Let's plug these numbers in.